Okay, so welcome back. In the last video we talked about the search process, we described the search tree and how we actually conduct search. However, implicit in that description was this idea of these fancy circles, these nodes that we're talking about constantly. Hopefully this is a terminology you've heard very frequently. But let's discuss then what is a node and why are we using these in the process of search. So a search node is essentially just a bookkeeping data structure. It's something as programmers we are using as an abstract representation in order to store important things that will aid us in search and allow our algorithms to behave favorably and to be able to find the solutions quickly. Now, we'll talk about strategies of how we're going to look at nodes in a future video, but right now we're just talking about what is this node? The root node, all the other nodes n, they're all the same. So towards this discussion, we're going to talk about the 5 things that search nodes essentially always store. So search nodes are extremely flexible and abstract data structures. So in terms of different algorithms or different implementations, you're free to store as many additional information you want that you might be able to make use of in order to inform your algorithms and to speed things up. However, every node still needs to store some essential information that is required by all search algorithms. So we're going to talk about what those 5 things are. So the first of those, of course, comes from the idea of what the node represented at the very beginning. For example, our root node was our initial state. It's where we began. So every node n in the search tree, no matter where it is, what it has to represent at some point in time, it has to store what state it actually corresponds to, what it's mapping to. This in a grid, for example, could just be a state 2, 3 as a location. So in addition to knowing where we are, right, which is the state, we also need to know where we came from. So if I am at some arbitrary node n in this tree, I'll choose this one, we also need to know from the previous state what action led to the current node n. Like what was actually taken, what was done in the real world problem in order to generate us where we are right now. So this is essentially the action that generated us. Now, what I think I'm going to write here is quite interesting about this, is that this is often implicit. So because we know, well, we often know, in most search problems, we know what the rules of the world are, we know what actions we can take, we know what we're allowed to do. Because of this, sometimes we don't even bother to actually store this in the state, simply because it can be retrieved with additional work based on looking at the rules of the world. So if I was at the state 2, 3, and then I'm in a new node at the state 2, 4, well, we know that we must have moved 1 in some direction. So sometimes this is implicit, but realistically it's still stored in the state. If it's more complicated actions, then you will definitely store it as an actual representation. Again, it's usually some form of abstraction that corresponds to it. If you moved north, maybe you just store an n, things like this, but that is very flexible. The next one though is corresponding, okay, great, so we moved north to this node. But in terms of the tree itself and the data structure and how we're going to search over this in a computer, we need a pointer to where we came from. We need a pointer to the parent P. This is the parent of this node here. So we call this the parent pointer. We often describe nodes as a parent, and then the nodes that it generates as its children. So this parent P would have 2 nodes, 2 children. Okay, and so now we know where we are, what action led us to this location, and where we came from. This information provides us context of where we are in the tree. But what is also additionally important, right, in the actual search process, trying to find a solution and a good solution, is we need to also track essentially our progress towards the goal. That is not just corresponding to our location in the tree, it's kind of corresponding towards where we are before we finally reach a goal, which is a little bit different. So the first one here is we need to see how far we've come. This is essentially the cost so far. So now let's talk about reaching the goal G here, okay? So from the root node, we will have traversed a series of edges. We've traversed this edge, and this edge. Each of these edges has either an assumed uniform cost of just 1, or sometimes, right, so I'll write in a few of those, but then you can also have problems which have variable costs. So different paths, different actions might have different costs. I'll do this, right, and so it never has to be the same. These depend on the problem itself. In this case, the path from the root node to the goal G, so this is now our current node N, which is the G. So this has a cost of 4. So the cost so far would be 4. If we were looking at the node we did before, this yellow node here, then that one would have a cost of 3 thus far. Now, on top of both just the cost so far, where we are, we also want to track the depth of our location in the tree. And this is really important for depth of node. This is really important for other cost tracking measures, as we'll talk about in the next video when we actually start looking at some search strategies and how we're going to go about choosing which node to generate next. So join me there. Thanks.